Welcome to Lab 1 of our Signal Integrity Basics series. To begin these labs, we lay the groundwork for understanding signal integrity, or SI, which is all about the quality of a signal and how accurately it represents its intended shape. In high-speed digital systems, ensuring the integrity of signals is paramount for reliable operation. Our objectives for this lab are to learn how to add components and build a basic schematic in HyperLynx LineSim, to effectively use the digital oscilloscope for signal analysis, to utilize measurement tools within that oscilloscope, and to create reports and find inter-symbol interference. At its core, signal integrity addresses how well a transmitted signal maintains its shape and the characteristics as it travels from a transmitting device to a receiving device. The goal is for the receiver to correctly interpret the data, which means the signal must arrive at its amplitude and timing intact. Many factors can degrade a signal, but for this introductory lesson, we will focus on key aspects like amplitude distortion and timing variations. Think of it like a conversation. If a message gets garbled or delayed, the listener might misunderstand. Similarly, if an electrical signal is distorted, the receiving chip might misinterpret the data, leading to errors or even failures in systems. Through this lab, we will learn to identify and begin to mitigate these issues. To begin our exploration, we will invoke Siemens HyperLynx SIPI, navigate to your SI Basics directory via Windows File Explorer, then double-click Launch HyperLynx SIPI's icon. From Browse LineSim Projects Open Schematic, locate the appropriate directory and open the file si_intro.ffs. Our goal is to simulate a signal traveling through a transmission line. To do this, we need to create a channel. We'll first add a transmitting and receiving device to each end, and then add a transmission line in the middle. Using the global bar, navigate to schematic symbols, IC buffers and MOSFETs. Select the IC I/O buffer, then drag the symbol. You'll need two of these symbols, along with the transmission line, which you can find in schematic symbols T-line and S-parameter, then transmission line symbols. Once placed, let's connect these symbols. Hover your mouse over the small circle on the left pin of TL1 until it turns into a plus sign. Click and drag to the small circle in the middle of the I/O buffer icon for U1.1 and create this connection. Using the same technique, connect the right pin of TL1 to the other buffer, U2.1. This generic buffer symbol needs to be assigned specific electrical models to behave as a proper transmitter and receiver. Double-click on U1.1 to open the Assign Models dialog. With this pin selected, click on the word Select in the Model Selection window. Then, from Libraries, find HLSI-workshop.ibis, then in Devices, HLSI Workshop, and finally, Signal IO1. Click OK to assign this IC model. Back in the Assign Models dialog, set the buffer settings for U1.1 to output, as this will be our transmitter. Next, select pin U2.1 from the Pins section and click Select. Again, choose the same library device and signal. Click OK in the Assign Models dialog and set the buffer settings for U2.1 to input, as this will be our receiver. We can now simulate a signal and compare what was sent over to what was received. To visualize this behavior, we'll use a digital oscilloscope. Using the global bar, navigate to Signal Integrity Interactive, then select Oscilloscope. Now, let's set up the oscilloscope for this initial simulation. Set the operation to standard, the stimulus to global edge rising edge, and the IC model to fast strong. This setting often represents the worst case scenario for signal integrity issues due to that fast edge rate. And finally, set the horizontal scale to 5 nanoseconds per division, then click Start Simulation. The oscilloscope now displays two waveforms. The smaller waveform in red represents what was transmitted, and the other waveform in green represents what was seen by the receiver. Notice the clear discrepancy. Both signals exhibit some overshoot where the voltage temporarily exceeds the target level. However, the received signal has a significantly higher level of overshoot and also shows quite a bit of ringing, which means that the signal oscillates around its final value before finally settling. This indicates that the signal's quality has degraded as it's traveled through the transmission line. Let's quantify the overshoot using the digital oscilloscope's measurements tool. In the measurements section of the window, select the waveform latest V U1.P003 at pin. This is our transmitting signal. Click on the second icon, which is for positive overshoot, and note the overshoot value. It should be around 74 millivolts. Now, let's measure the overshoot for the receiver signal. Select the other waveform, V U2.P003 at pin. Click on the positive overshoot icon again, and you should observe a much higher overshoot, around 872 millivolts. This significant difference highlights the signal integrity problem. With such pronounced ringing at the receiver signal, it's clear that action is needed. Typically, to minimize ringing, engineers consider the 4 T's of signal integrity: topology, termination, technology, and T-line parameters. In our current setup, the topology is a simple point-to-point net. This is not something that we're going to alter here. Termination will be discussed in another lesson. Technology would require a change to the slower edge rate driver. Assuming a fixed driver and edge rate, let's start by looking at altering the last T, transmission line parameters. The length of the line is one factor that would reduce the overshoot, but the impedance of the transmission line is another factor. Minimize the digital oscilloscope window and head back to LineSim. Double-click on TL1 to open its properties. In the Edit Transmission Line dialog box, go to the Stack Up tab to change the trace length. Let's change the length to 2 inches, then click OK. Going back to the digital oscilloscope again by navigating to Signal Integrity Interactive Oscilloscope, we'll click Start Simulation one more time. Now, let's compare the latest results with our previous simulation. With latest results toggled on, toggle previous results on and off to compare the waveforms. You should observe that the overshoot in the latest result is significantly reduced compared to the initial simulation. This demonstrates that a parameter like trace length can have notable impact on signal quality, though it may not be the complete solution. Next, we'll investigate intersymbol interference, more commonly known as ISI. ISI is a phenomenon in digital communication where symbols or bits transmitted over a channel interfere with each other. This interference makes it difficult for the receiver to correctly interpret the current bit because of the residual energy from the previous bits. ISI can be caused by channel bandwidth limitations, reflections, and other signal distortions. The value of ISI quantifies the amount of signal distortion. Reporting ISI in high-speed PCB designs is crucial because it directly measures how much the channel limits signal integrity, and by identifying the extent of ISI, engineers can determine what improvements are needed to maintain reliable data transmission. To analyze ISI on this channel, we'll use the SI Preview Wizard. Using the global bar, navigate to Signal Integrity SI Batch Analysis, then click on SI Preview Wizard. Set the controller to U1 and click Next. Select All to move all the available nets to Nets for Analysis. Then click Next. This screen shows various simulation settings that can be varied, such as termination, stimulus options, and other coupling settings. Termination refers to the practice of ending transmission lines with devices that match the characteristic impedance of the line to prevent reflections. This is a topic that's covered in another lab. For now, click Next. The driver-receiver cases screen allows you to specify cases for the driver-receiver combination. For now, we'll leave them as they are and click Next. Once you arrive at the Reporting Options tab, click Run. Once the simulation is complete, a summary report window will appear. Look for the Pulse Response Summary section, where you'll find a max ISI value. This value is a direct indicator of the signal distortion present in the current channel. Now, let's explore eye diagrams, a powerful visual tool for assessing overall signal quality. An eye diagram is created by overlaying multiple signals of a digital signal on an oscilloscope. This involves capturing segments of a long data stream driven by a master clock and superimposing them to visualize the signal's behavior over time. The resulting pattern resembles the shape of an eye, hence the name. The vertical axis represents voltage levels, while the horizontal axis represents time, typically divided into bit periods. A wide, open eye indicates good signal integrity, while a closed or distorted eye suggests significant problems. To begin, we'll open a new schematic file. Invoke HyperLynx SIPI again, following the same steps as before, by choosing the HyperLynx SIPI launch icon. Then choose Browse LineSim Projects, Open Schematic. Browse to the appropriate directory for this lab, then find the file idiagrams.ffs. Click Open and investigate the channel. Open the oscilloscope to review the differential signal at the transmitter and receiver. Navigate to Signal Integrity Interactive Oscilloscope. Let's set up the simulation for this eye diagram. We'll set the horizontal scale to 2 nanoseconds per division, the vertical scale to 100 millivolts per division. We'll enable the rising edge, set the IC modeling to fast strong, and in the pin section, we'll enable R1.1 at pin / R2.1 at pin. These will represent the differential receiver pins. Click Start Simulation. Observe the oscilloscope display. You'll likely see significant ringing and reflection at the differential signal, indicating a challenging channel. Now, let's look at the individual positive and negative resistor lines. In the pins section, disable R1.1 and instead enable R1 and R2 waveforms. Probing these nets at R1 and R2 allows us to see the individual components that combine to create the differential waveform. Now, let's configure the simulation specific for an eye diagram. Select Operation Eye Diagram, then select the Configure under Eye Diagram. We'll set the sequence to 8 bits by 10 bits, a common encoding scheme. Then we'll change the bit rate to 1.5 gigabits. This will automatically set the bit interval to approximately 0.6667 nanoseconds. Then we'll set the sequence reps to 200, and we'll set skip first to 2 bits, therefore skipping the first 2 initial transient parts of the series. We'll set the number of eyes to display to 2, and then going into the iMask tab, we'll set the mask name to the system SATA Gen 1 IRX. An iMask defines a forbidden region. If the signal crosses this region, it indicates a failure. Then we'll click OK. From the pin section, ensure that R1.1 is active again, then set the horizontal scale to 200 picoseconds per division and the vertical scale to 100 millivolts per division. Click Start Simulation. Once the simulation completes, you'll see a full eye diagram. Now enable the eye mask by clicking the corresponding icon. Notice that the eye mask is likely not perfectly centered within the waveform. This needs to be adjusted horizontally to fit within the center of the eye opening. Click Adjust Mask, then click and drag in the waveform view to drag the center of the mask into the eye opening. Once the center of the eye opening cleanly selects around the mask, you'll likely notice that the waveform does not pass. This is often due to overshoot, where the waveform exceeds maximum allowable voltage at the receiver, indicating an interference at the horizontal boundary. This failure suggests that the long differential pair, especially with loss initially ignored, is causing significant signal degradation. Minimizing the digital oscilloscope and returning to the LineSim window, let's address this issue. We'll first enable loss in our simulation, as real-world traces are never ideal. Select Simulation Setup, Loss, Enable Loss. If by chance this option isn't immediately visible, use the search bar and type Enable Loss, then right-click and unhide it. Return to the digital oscilloscope and click Start Simulation. This time, you should observe that the overshoot is mitigated, but the eye has likely closed slightly. While an improvement, the waveform is still failing the eye mask. This continued failure is primarily due to ISI. Since we've now accounted for loss, it's time to look at altering the long traces to further reduce the signal degradation. Minimize the digital oscilloscope and return to the LineSim window. Double-click on TL3 to invoke the Edit Transmission Line window. Note that the current differential impedance is around 95 ohms. Our goal is to change trace properties to minimize loss while maintaining this approximately 100 ohm differential impedance target for this channel. Let's change the trace width to 8 mils and the separation to 20 mils. Then click on TL4 from coupling regions to change its trace width to 8 mils to match its pair. This adjustment should keep the differential impedance around 93.2 ohms, still close to our target, but with improved loss characteristics. Click OK. Then open the digital oscilloscope again and click Start Simulation. You should observe now that the eye is passing. This demonstrates how crucial it is to consider both loss and proper trace geometries to achieve a wide eye opening and ensure that reliable high-speed data transmission is possible. To conclude this foundational lab, we've covered essential signal integrity concepts. We've learned to build a basic schematic, simulate signals using the digital oscilloscope, and quantify issues like overshoot. We explored inter-symbol interference and its impact on signal quality. Most importantly, we gained practical experience with eye diagrams, understanding how to set them up, interpret their results, and make design adjustments, like enabling loss or optimizing trace parameters, to achieve an eye opening and meet signal integrity requirements. This foundational knowledge is critical for designing robust and high-performing electrical systems.